Hi, I am Francis Arody, professor at the University of Brasilia, and I will present the work entitled "A New Time Domain-Based Busbar Protection Algorithm," which was developed with Eduardo Pastor Ribeiro and Professor Cleber Melvin Silva and Professor Felipe Lopes. So, I must begin saying that the growing electricity demand led to the construction of more transmission lines, inclusion of more power transformer, and connection of more feeders in bus bars. And that means that short circuit levels are higher. In the scenario, the speed and selectivity of bus bar protection schemes are very critical in order to in order to guarantee the stability of the power system. And also, these protection schemes are traditionally based in the differential and directional principles, and this work uses these principles simultaneously, and we apply them into incremental quantities which are calculated with a half-cycle window. These incremental quantities are referred to the currents. In any case, any protection scheme must provide fast operation for internal faults, security for external faults, and adaptability for evolving faults. So, in order to explain the proposed protection algorithm, I will use this simple power system where I have a bus 1, bus 2, and bay 1, bay 3 are connected to the bus 1, and the bay 2 is connected to the bus 2. These buses are interconnected through a tiebreaker, and when a fault occurs in the bus 1, for example, the currents are calculated. The differential current is calculated as a sum of the contributions, and also when a fault occurs in the bus 1, for example, all the contributions have the same polarity. All of them flows into the bus 1. Also, it must be noticed that here I have two cities and two current transformers, and here the current transformer CTB1 is connected to the bus 1, and the current transformer CTB2 is connected to the bus 2. But the CTB1 measures the current coming from bus 1 and entering into bus 2. And the CTB2 is connected to bus 2, but it measures the currents entering into bus 1. So if the fault occurs at bus 1, the CTB2 provides currents with the same polarity of the other contributions. So it's important to know that because it provides information about the bus, the faulted bus, as well as the feeders that must be disconnected. So here we have our proposed method, and here the method consists of the application of these concepts, differential and incremental principles, but applied on the incremental currents. So the incremental currents are calculated with a half-cycle window, and there is a motivation for that, and it will be shown in the results section. And also we can calculate an incremental differential current, which is the sum of these incremental currents. And also we can have here a disturbance detector. We included a disturbance detector calculated as in this expression. And these variables are used, these signals are used to the formulation of the logic, or the protection logic, of the proposed method. So here the secondary currents of current transformers are previously processed, and the currents are used for the calculation of incremental currents, and the output is used for calculation of these blocks. Here we have the disturbance detector. Here we have that we calculate incremental currents, and we monitor that these values are higher than a minimum pickup, and also if the sign of these incremental currents are the same. Also, we verify that if the absolute value of the incremental differential current is higher than the minimal value, and also if the sign of this incremental differential current is the same of the sign of individual incremental currents. If these conditions are satisfied, we have an internal fault, and in this case, we must know the status of circuit breakers and disconnect switches in order to define the feeders that must be disconnected. Also, we must monitor the polarity of these currents entering into the faulted bus. On the other hand, in case of an external fault, if you have an external fault, the polarity of the current of the feeder where the external fault occurred will have an opposite polarity. It will be opposite to the polarity of all the other signal. In this case, we will have an external fault and the operation of the relay is blocked. Nevertheless, we can experience the evolution of an external fault into an internal fault, and in this case, it was identified that there is a change in the polarity of the differential current, and it acquires the same polarity of the initially faulted feeder. And if this event occurred, if the polarity of the differential current change, we will have an internal fault, and in this case, we must send the trip of internal fault. So, in order to test the proposed method, several cases were performed, as shown in this list, and all of these results I fully explain in the paper corresponding to this work. Here we use a double bus single breaker 5 disconnect switches configuration, and here this configuration is known by its high flexibility degree. And here we have 4 transmission lines and 2 transformers. And traditionally, the differential protection implements the protection zones logic. But in our case, as mentioned previously, we don't use this logic. First, I have an internal fault at bus 1, and we can see that all of incremental currents and differential incremental current have the same polarity. The fault occurs at this instant, and the internal fault is identified in less than 2 milliseconds. Also, we can notice that the differential incremental current has the same polarity of the current transformer CT1V2, which is connected to bus 2, but it measures the currents entered to bus 1. Thus, it is confirmed that the fault occurred at bus 1, and all the feeders connected to this bus must be disconnected. By the way, this is the last step. We must identify the feeders to be disconnected, and for that, the status of the circuit breakers and disconnect switches must be known in order to disconnect all feeders connected to the faulted bus. Now we have an external fault which causes a high degree saturation of the CT, and the external fault occurs at feeder TL1 of blue line here. And it can be noticed that the polarity of this incremental current is opposite to the incremental current of the rest of feeders, as well as to the incremental differential current. In this case, the external fault is identified. Here, in this case, an external fault initially occurs at this instant in phase A at feeder TL1, transmission line 1, and it causes the saturation of the corresponding CT. After that, the fault evolves to an internal fault at this instant here, involving now the phases A, B, and the ground. Here is the result corresponding to the phase A, and here is the response to the result corresponding to the phase B. Here it can be noted that after the external fault inception, the signal whose polarity is opposite to the rest is only of the feeder TL1. Here, the blue line. In this case, the external fault is recognized and the operation relay is blocked. Nevertheless, when external fault evolves to an internal fault, the polarity of the incremental differential current becomes the same of the initially faulted signal here. So the internal fault is recognized. On the other hand, according with the results of phase B, the behavior is similar to an internal fault, to a simple internal fault. That is, all of incremental signals have the same polarity and internal fault is recognized. That is because this phase is not involved in the first moment when the external fault occurred. Now I repeat the result of the simulation of an external fault with CT saturation, and in here now the proposed technique will be tested, but by using a one-cycle window for the calculation of incremental currents. The result is as shown. It is hoped that the algorithm does not operate in this condition. However, it can be noticed that the function erroneously identified a fault, an internal fault, at approximately at 95 milliseconds. It occurs because of the window size that is one cycle, and it causes that incremental differential current changes its polarity due to the saturation of the CT. With a half-cycle approach, the only signal which must have an opposite polarity in relation to the rest corresponds to the faulted feeder. All the others, including a differential signal, must have an opposite polarity, but it does not occur with the one-cycle window, which changes polarity and becomes equal to the polarity of the initially faulted feeder, and that would represent an internal fault, or the evolution of the external fault to the internal fault, and in this case it is wrong. Now the proposed method is tested for different values of fault resistance, and we can observe that the operation time is higher as the resistance is higher. Here we simulate fault from 0 to 300 ohms, and we can see that the difference between the best case without fault resistance and the worst case with 300 ohms is only approximately only 1 millisecond. So it means that the algorithm provides a good response for these scenarios, even in presence of a high resistance fault. Here we assess the impact of the sampling frequency on the operation time for the proposed technique during an internal fault. In that sense, the function was tested for 16, 32, 64, and 128 samples per cycle. It is clear that the operation time is larger as the sampling frequency is lower. Nevertheless, with 16 milliseconds, we can obtain an operation time lower than a quarter cycle. Also, it must be noticed that the relation between the cost and the benefit is less relevant as the sample frequency is higher. Finally, between the main conclusions of this work, we can say that the proposed algorithm successfully works by using the directional and differential principles for busbar protection application. By using the incremental differential currents calculated with a half-cycle window. The window size choice is critical for leading with evolving faults. On the other hand, this technique needs the status of circuit breakers and disconnect switches for correctly identify the feeders to be disconnected in presence of a fault. But contrarily to the traditional differential technique, there is no need to construct a protection zone logic. The results show that the proposed method provides a fast and robust operation, even for critical scenarios. Finally, once this technique uses traditional concepts, it could be represent a suitable alternative for practical application. Thanks for your attention.